Okay. So thanks everyone for joining today's AI seminar at ISI. It's my pleasure to introduce Professor Yu Su from Ohio State University. So Professor Yu Su is an assistant professor at OSU, where he leads the natural language processing group, and also he's a senior researcher at Microsoft Semantic machine. He got his PhD from UCSB and also bachelor's degree from Tsinghua University, both in computer science. I think Professor Yu Su has made lots of significant contribution recently on conversational AI and also question answering systems. For example, his work at Microsoft has led to a new conversational interface for Microsoft Outlook, which is what we are all using. And also he has published over 30 papers at premier AI and also NLP conferences, which has been recognized with awards such as Outstanding Dissertation Award from UCSB and also Best of CDM selection in 2019. So let's welcome Professor Yu Su to share with us about the new emerging frontiers of conversational AI.
Thanks, Mahal. Thanks for the nice introduction. Okay, let's get the sharing going. Can I see the screen?
Yeah.
Great. Let me just tune the Zoom windows a little bit so that I can see everyone. Okay, great. Good morning, everyone, and good afternoon to people on the East. So thanks for having me here. I remember actually 5 years ago, I also gave a talk here at ISI. And that was, like my very first invited talk. So I'm very glad to be back here today, even though this time is virtual. So in the past 5 years, I've spent a significant part of my time on conversational AI, and including problems like, dialogue systems, question answering, and semantic parsing. And in addition to my academic work, in the past 3 years, I was fortunate to be working in the Microsoft Semantic Machines team. And earlier this year, we shipped a new conversational interface to Microsoft Outlook, which is now accessible to millions of Outlook users. So I was fortunate to have some frontline production experience as well. And from my experience, I believe conversational AI is currently at a tipping point. On the one hand, there is growing consensus in both industry and academia on the promise of conversational AI as a universal interface that can seamlessly integrate a wide range of data and services, or even as the interface to the whole computing world. And systems like Alexa and Google Assistant have been cultivating a huge user base for such language interfaces. But on the other hand, the current generation of conversational AI techniques has yet met the high hopes, and they still present significant limitations in their expressiveness, contextuality, and trustworthiness, among many other things. Therefore, in recent years, there have been a lot of exploration on how to push conversational AI up to its potential. And in this talk, I hope to introduce several research frontiers emerging from this recent exploration. So I'm not sure if I can see raised hands, but please feel free to interrupt anytime if you have questions. So we say natural language is our most natural way of communication, and we can express virtually everything in natural language. So it naturally has the potential to become the universal interface for human-machine communication. And more practically speaking, there are just so many things that are easier said than done. So having conversational interface could bring a lot of values to users. For example, we know many of us are actually having more meetings than before during the pandemic, right? And the most time-consuming part of scheduling a meeting is to find a time that works for everybody. And with a conversational interface, we may just need to say, like schedule a meeting tomorrow with Megan and I are both free. And under the hood, the AI agent can check the schedule of everyone and propose the best time, satisfying all the other constraints like tomorrow and when everyone is free. And that could save us a lot of back and forth. And similarly, we can use natural language to query relational databases, query Excel tables instead of having to write SQL queries and things like that. And the last two examples here are also interesting in the sense that they are seamlessly connecting multiple services and domains to reach a user goal. Like for this example here, we need to first query the user's calendar to find like the time and location for the flight. And then you need to pass this information to another app, say a map or a navigation app to get the traffic. So it will be tedious for us humans to do this, which involves a lot of clicks and open and close a lot of apps and things like that. But if we can just say in natural language like this, it will be very convenient. So conversational AI is great, but why can't my Alexa do any of this yet? So next, I will provide a perspective of why conversational AI is hard. We'll see that in conversational AI, we need to deal with three long tails. The first one is the long tail of linguistic variation. So for the same thing, different users can express it in very different ways. And even for the same user, they can express it the same thing in different ways at different times. So for asking for a calendar summary, the most common way to say is maybe show me my calendar. But the slightly less frequent, but still very frequent way to say it is what's my schedule look like? And there are many other ways, like summarize my day for me, or even like change of mind, like what's on my plate today. So, and in reality, it's a rather heavy or fat tail. So if the agent cannot understand or properly handle some of these, it will hurt the experience of a significant portion of your users. So the second long tail here is the tail of capacities. Even in a single domain, like just say calendaring, there could be many different capacities different users would want. The most common one may be just show my calendar, and you could schedule meetings in different ways, and you can query your calendar, or you can check the availability of people. And there could be highly compositional ones that's connecting multiple domains from calendar. And again, this is a heavy tail. Finally, the third long tail we need to deal with is context. We can see that the same user audience could mean totally different things under different contexts. For the user audience, how about 3 p.m.? If it's under a meeting creation context, then it means to change the start time of the meeting to be created. If it's instead in a weather querying context, then it's to query weather for another time. So the interpretation of the same user audience will be totally different. And of course, there are all kinds of contexts. Like in this case, you need to resolve the pronoun she here in the user audience to be Megan from the context. So preference resolution. And here you need to get the time and the location from the context for this weather query. So it's another dependency on context. And again, there is a very heavy tail on context like this. So it's these 3 different long tails that make conversational AI particularly challenging. Then how is the standard approach, like that used in Alexa or Google Assistant, is modeling such language interfaces? The standard approach, which is often called slot filling, divides the world into a set of predefined domains. And each domain contains a set of predefined intents, and each intent contains a set of slots. So then we could have like a smart home domain with the intent corresponding to, say, turning on and off the lights. And in the same domain, we can have another intent corresponding to setting the timer. And in a different domain, we can have some different intents. So basically, within each domain, we can support utterances up to a certain complexity like this. However, when things become a bit more complex, such representation turns out to be very hard to model them properly. For example, if after this first user utterance, first round of interaction, the user follows up with another request, which actually involves interacting with another domain, it becomes unclear anymore how to represent it properly with slot filling. So in the rest of the talk, I will introduce 3 emerging frontiers of conversational AI that aim to address different aspects or shortcomings of the standard approach. So I will first introduce a new representation for conversational AI called dialogue as data flow, which is fundamentally different and much more expressive than the standard slot filling approach. I will then talk about the setting where a conversational agent needs to cover a wide range of domains. And this is needed if we want to build a universal language interface that can do many things at the same time. And we will base our discussion on the problem of question answering on large-scale knowledge bases. So we have knowledge bases containing hundreds of domains. And last but not least, I will introduce a new learning paradigm for conversational AI, where the agent can autonomously and continuously improve itself by directly learning from user interaction. Okay, so let's start with the representation part. Over the past 3 years, the Microsoft Semantic Machines team have been trying to rethink conversational AI, or more specifically, task-oriented dialogues. And this paper, published in Transactions of ACL 2020, describes some of our thinking with a focus on dialogue representation. And you may see many familiar names here, like Dan Klein from Berkeley, Percy from Stanford, and Jason Eisner from Johns Hopkins. But this is truly a teamwork by a great team of researchers, engineers, program managers, and data specialists, and over a long horizon of time. And this is also the same technique that is powering the new conversational interface of Outlook, which we will demonstrate later. So what is the Semantic Machines view of conversational AI? In a nutshell, we believe a dialogue is really a collaborative process between a user and an agent to write a program. And this program records everything that has happened in the dialogue. So given a new user utterance, the agent's task is to synthesize the appropriate continuation of the program based on the context. And because we are using programs as the mini representation here, which is much more expressive than simple intents and slots, so it becomes easy and natural to connect different domains to model the previous interaction. And there are 5 key ideas behind our technique. The first idea is dialogues, the recognition of dialogues or programs. So the agent's task is to synthesize this program. And then we recognize that complex tasks are built from simpler ones. So everything in our system needs to be designed in a way that is compositional. And we also recognize that meaning really depends on the context. So we develop various kinds of meta computations that will allow us to model different information from the context. The first idea is that we believe things will go wrong, and a robust conversation agent needs to have various exception handling capabilities in order to really serve users in practice. And finally, we believe that a system should always tell the truth. So we have this dynamic grounded generation technique that will make sure our agent will never lie. Next, I will briefly introduce each of these 5 ideas. The first idea, dialogue as program synthesis. See, from this perspective, we can actually also think of the standard, intent and slots representation as programs as well, but they are rather simple ones. Like for this intent of turning on the lights, you can have a function, right, called turn on lights, and without any argument here. And for another intent set a timer for 5 minutes, you can have another function called set timer with the argument, which is the time here. But the thing is, when things becomes slightly more complex, like what time am I getting coffee with Megan? You would need to define some rather complicated functions like this if you follow the intent and slots framework, right? So the real issue here is that we are trying to solve inherently combinatorial problem by enumeration, which is, of course, not gonna scale. So in our representation, we will represent it as a real program where each statement here corresponds to a function call. So this is the first function call. This is a name and this is the argument. And the functions can be nested. Like this argument here is actually itself a function call with the name like, which is to support fuzzy string match. And then the execution results of each function call is stored as variables like this. And such variables, such stored execution results can be reused in subsequent function calls to support conversationality. And it goes on like this. And you can see a nice one-to-one correspondence between the user utterance and the program here. But now, instead of just intent and slots, here we have a complete compositional program that captures everything about the user utterance. And a simple note here, the describe here corresponds to our generation system. So if you call something with describe, it will generate an agent utterance to respond to the user.
Can I interrupt to ask you a question here?
Yeah, sure.
Doesn't the same problem that you outlined in the last slide, shouldn't that also apply to here for the find event thing that should be find event by subject and attendees?
Not really. So you will only, in the previous representation, you need to have a function for basically every combination. So you need one for find the time of an event with the subject and the attendee. And you need another one for find the time of an event with just the subject or with multiple attendees. And you need another one for find the location of an event with the same arguments. So you need a separate intent for every combination of those. Here, you will only have one find event function. And then you can define it in a nested way. So this corresponds to your underlying API, right? You have an underlying API that says, okay, you can for the event object, you can have a list of you can have a subject, which is the string. You can have a list of attendees and the type of each attendee is like this. So you can define your function based on the API. And then for each argument here, like attendees, you can define it in a nested way that So the attentees field corresponds to a list of objects with type recipients, and you can get the recipient from using another function call and things like that. But the point here, you will only have one function called find events.
So what if you want to find an event I want to find events that start at 10 o'clock? That needs a different function, right? Because it needs a different API.
They are actually they are the same API. So we are not listing every argument of this find events function here. For simplicity, we are only listing these two arguments. But in reality, this function has a complete list of arguments.
But that could have been true before too. That the function in previous, it just seems like it's the same thing. I mean, you can abstract away or not, but like you can have optional arguments or not in both cases. I mean, whether you decide to, yeah, it's true. It doesn't scale it if you actually change the name of the function. That's why you want to have the ability to have 0 or more entities. But I don't know. It doesn't seem like this has saved you very much, unless you say. I mean, the fact that you're returning an object instead of a primitive is. I'll give you that one. But the rest of it doesn't seem like it seems like you still potentially have a scaling problem.
Mm-hmm. I see the point here. Yes. So we can definitely get that one. That we are executing this function calls. We are storing the execution results as variables, and we are reusing them to get better conversationality. I think in principle, you could define the intent slots framework in a way that can get something close without the results reusing part. If you just aggressively use default values for the missing arguments probably. But we will see later that this is just a part of our whole representation. So it's like it's in the end, it's really all these things that come together that make it work that well. So it's not any single thing here that makes it work. I hope that answers the question to some degree.
It's okay. Yeah, we should go on.
Yep. Right. So let's see. So that's the first idea. So really the state representation for the dialogue here is a program. And then with this representation, we'll see that even for very complex utterances, very compositional ones, we can easily represent it. So here, the utterance is what's the temperature going to be for my coffee with Megan, slightly more compositional than before. So we can, for the top part of the corresponding program, we'll see that it's exactly the same as before, which corresponds to the my coffee with Megan part. But then if we want to know the temperature of this corresponding to this event, we can just reuse the execution results from before, and then get the location and time from the results to do a weather query, and then we can get the temperature. So it's highly conversational in this way. And under the hood, what we are really representing the dialogue state here is a new data structure called dataflow graph. So it's a more structured and compact way to represent what's going on in the dialogue. Here, each node in the graph, dataflow graph, it corresponds to a function call, and it also holds the value of its execution from its execution, right? And then the edges here basically represent the dependency between the nodes, where basically it's the arguments used in the corresponding function call. So it's similar to the computation graphs in TensorFlow. And a clear advantage of this representation is that there is clear execution semantics. So if you want to evaluate any node, we just, like, let's say we want to evaluate the find event node here. We just need to evaluate all of its parent nodes following the arrows and get the value and use these values as arguments to call this function. And then you will get the execution results for the target node. I think there's a raised hand.
Yes. It was Alex, right? Can you type in your question if you want to ask it?
Should we maybe continue for now? Yeah, sorry, Mohal, I would like to moderate. Sorry to interrupt like that. And so that's the case when the user just want to express a very complex intent in the same turn. But if it's the more natural case where the user expresses the same thing across different turns, under this representation, it will still be the same. So if the user first asks about the events, then we synthesize the program like this. And then if she follow up with the weather query, then we can just reuse the previous execution like this. So it's exactly the same, except this additional generation statement. And under the hood, the data flow graph will also be constructed in an incremental way. So after the first turn, we will construct this part of the data flow graph. And after the second turn, we'll extend this data flow graph with the new information like this. Okay, so the third idea is about context. We know that the same user audience could mean very different things under different contexts. Like if there's no context, then what will the weather be like? Will be most likely asking for the weather at the location here and about the time now. However, if there is some context, like we already have some retrieved some events in the context, then if that's followed up by the same user audience, then it's asking for the weather about that location at that time, right? But if we ask the agent to directly predict these different programs based on the same user audience but with different contexts, it will be very challenging because there could be very, very different contexts, and the agent is looking at the same user audience. So it's going to take a lot of annotated data to properly learn that. So our first meta computation is a way to handle such references. So instead of directly annotating these programs with their denotation, like now or here, we annotate it with this reference call. Refer here is a function, and it takes as input a constraint. So what this program really says is that all we know based on the current user audience is that it's asking for weather. And it's asking for the weather about the most salient location at the most salient time based on the current context. And then you can, the agent can look at the data flow graph constructed so far, and based on the constraints, like we know this is the place, we know this is the time, and we match on the data flow graph to find the best matching values that satisfy these constraints. So the key point here is that now, at least in the eyes of the planning model, the plan for these same user audience but different contexts will be exactly the same. So that makes the learning much easier for the planning model. So that reference is really about reusing values from the context. And it turns out that values are not the only thing that can be reused from the context. So we can also reuse computation as well. So let's look at this example. We start with, do I have any meetings today? And then followed by, what about tomorrow? So what this user audience is really trying to do is that I want to do the same thing, like query for my meetings, but instead of today, I want to query my meetings about tomorrow. So I want to do the same thing again, but with a different argument. If we annotate this naively, then we will just annotate its extensional form, basically. So then we say tomorrow and find the event that correspond to tomorrow. But here we are creating a discrepancy. Like really the input audience is very simple, but the agent is asked to predict something much more complex than the input audience. And it needs to understand the whole context in order to predict this plan correctly. And of course, there could be many different contexts for the same user audience. And in every of these cases, the agent needs to predict a different plan based on the context. So our proposed revision meta computation works like this. Instead of directly predicting this extensional form of the plan here, we instead predict a so-called intentional form, where we define this special revision function that basically has 3 arguments. The first argument is the root location. So it's the root location of the subtree where we want to revise in the current data flow graph. And the second argument here is the old location. And the third argument is the new value we want to replace the old location for. So look at the example here. We will find the root location will be the find event node we have constructed in the first term, and the old location is a date which corresponds to today here, and the new argument we want to replace today by is tomorrow, right? So in this way, we are reusing the previous data flow graph, but doing the minimal thing to fulfill the user's request. And if we look at this seemingly complex program, it's really just doing exactly what the new user audience is asking us to do. So the user says, what about tomorrow? Then the corresponding plan is, okay, we will find the most salient action from the context, and we will replace the location in that action with the constraints of a type date, which is all we know from the user audience, with the new value called tomorrow. So in this way, we bring the representation much closer to the user audience and makes it context free. Okay, so the fourth idea here is that we know things will go wrong in a real system. And so we need very strong exception handling in the system. Like for example, for simple utterance, like set up a meeting with Megan here, there could be multiple different errors. You may find that, hey, there are multiple Megans in your contact list. So the agent doesn't know which Megan it should choose. So there is a disambiguation. And maybe there's no Megan at all. or the API is down, so there's a timeout API error. Or the user simply has not supplied enough information to call this API, so there is a missing slot error. Then we design this exception handling mechanism so that we can predefine these exceptions and then catch them and generate the appropriate agent response corresponding to each one of them. So if this is a disintegration error, then the agent could say, did you mean Megan Bowen, which is one of the Megans? And then the user could respond with something like yes. Then what will happen is that we will call the revision meta computation we just talked about before, and that will revise the previous plan with the new information to confirm that this is Megan Bowen, and then get the dialogue going. So this is how the exception handling and the revision meta computation will go along very nicely. Finally, we think the system should never lie, so we need truthful generation. It's very clear why we need this. Like, if when user says, when is my package coming? If the agent just respond with some arbitrary things like, it looks like it should arrive Friday, but there's no way for the user to validate whether this is true or not. And that if it turns out to be false, then it will greatly hurt user experience. So and the agent could generate 1,000 different responses here, but really the response should be grounded in the real world by hooking up with some APIs to know what really is coming. So with the data flow graph, it makes it pretty straightforward to guarantee the truthfulness of the generated agent utterances. So remember we talked about this describe call, which is to describe a value. And we know in the data flow graph, how exactly this value is derived. So when trying to generate a appropriate response, we can traverse the corresponding data flow graph and fetch all the needed values from the data flow graph and generate a response at the proper level of specificity and verbosity. And there are some less favored responses we can also generate, like we can generate a less verbose one, but in this case it's less preferred because the users cannot validate whether the agent properly understands the utterance and is getting the information from the correct location and time. Right, so that covers the 5 key ideas behind the semantic machines technique. And we are also, with this paper, we're releasing a new data set for task-oriented dialogues, which we believe is the largest data set of its kind so far. And it contains more than 40,000 dialogues. And one thing to note about this data set is that it's a subset of the real data set we're using to power the real product, which is the Outlook conversational interface. So it's not just some synthetic data set we release for the community. And here are some simple examples from the data set, but I think we can skip this. So here is a simple demo. And I just made it on my phone myself. So it could be a bit naive, but I think it shows the gist of this technique.
When is my last meeting tomorrow? Right after that, schedule a meeting with my manager. It's about intern project brainstorming and also invite Percy and Jason.
So it can understand fairly complex requests like that.
Jason Wolf, not Eisner.
Oops, sorry.
With my lab project brainstorming, and also invites Jason Wolf, not Eisner.
So here it's like it's a revision call to the previous thing. Here I want to replace Jason Wolf, replace Jason Eisner with Jason Wolf.
Actually, sometime after 9 p.m. would work better for me. Yes, looks good. Book it.
Okay, yeah, so that's a demo. And if you're using iOS Outlook on your phone, I think you should be able to try it yourself right now. So that basically concludes the first part of this talk. Any questions so far?
So there were a number of ASR errors in the demo. Does the data set have ASR errors or options or things like that, or is it all gold transcription?
Great question. So the ASR is not, I think we're largely using the provided Microsoft services for ASR. So it's not our team that's creating the ASR from scratch. And in the data set, no, there's no, I believe there are a few, but I don't think there are a lot of like such ASR errors. So it's mostly code.
Was it created by speaking?
No. Well, most of it, no. But that's an active area of investigation right now. Any other questions? Okay, great. So let's move on to the next emerging frontier, which is broad coverage. For this, we will be focusing on the question answering on knowledge bases problem. We know that modern knowledge bases are extremely large and broad. So like for Freebase, there are over 100 domains, 45 million entities, and 3 billion facts. And the Google Knowledge Graph is even way much larger than that. In 2020, I believe, they claim that we already have like 5 billion entities and 500 billion facts. So these knowledge bases or knowledge graphs, they usually contain two parts. One is the ontology part, like the top part here, and which consists of classes or types or concepts, whatever name you prefer, and the relationship between these concepts. And then there is the model part of this knowledge graph that corresponds to the realization of these relations. So containing the real entities and the facts between the entities. And when we are trying to do semantic parsing or question answering on broad coverage knowledge bases like this, we'll realize that the i.i.d. assumption, which typically assumed in conventional machine learning, doesn't hold anymore because it's simply impossible to collect sufficient training data that will cover everything that could happen at test time. And also, like the test distribution is really a moving target, and you don't really have a good way to estimate what that distribution really is. So therefore, in this work, which is a collaboration between OSU, Army Research Lab, Stanford, and the UC Santa Barbara, we published at the Web Conference 2021. We argue that for a KBQA model to be practical, it should be built with non-i.i.d. generalizability. In particular, we argue that there should be 3 levels of generalization. Let's assume this is the training data we have. Is the user utterance or the question and the corresponding program. Here, the program we use the Lisp representation. So then basically each of these is a function call, and it's followed by arguments which correspond to relationships or entities, right? So for i.i.d. generalization, we mean that these questions, their corresponding programs are basically seen during training time, right? And there could be slightly more challenging setting of compositional generalization, where you have seen all these schema items during training, but their composition, the specific composition is novel. So you have not seen during training, and you still want to generalize to this composition. And finally, there is zero-shot generalization, where the program could contain schema items that are not seen during training. So how can we generalize to that case? So that's the 3 levels of generalization we argue that the practical KBQA model should have. And then we generate this large-scale data set for study of this non-i.i.d. generalization for KBQA. And it's a large data set containing like over 64,000 questions. And also it's very broad coverage. It covers 86 domains and over 3,000 different relations. And here are some sample questions from the data set. You can see that each question could cover multiple domains, and it could be of different complexity and different number of answers. And there could contain functions like superlatives, counting, and comparatives in such questions. And we split the data set in a way that allows us to evaluate compositional and zero-shot generalization. So in the interest of time, I won't be able to talk too much technical details here, but I just want to highlight 2 technical challenges arising from such a setting. So it turns out that schema linking becomes a huge challenge when you have a broad coverage schema like that. So for this question here, it can reasonably correspond to many different relations in your schema. It could be in the games domain, the designer relation, or it could be in the computer domain, the key designer, or the sports domain, the golf course designer. So you need to really thoroughly understand the question and each of these relations to correctly link the correct schema to the question. And a potential solution for this problem is the so-called joint language schema understanding by BERT, which we will briefly talk about later. And then there is also a large search space problem, especially for complex questions. So you will essentially face combinatorial explosion on a large graph like that. So how do you navigate this search space in an intelligent way that will allow you to answer complex questions efficiently? So I'll just briefly talk about BERT-based joint encoding for handling the schema linking problem, which starts to be widely used in text-to-SQL parsing, but not so much in KBQA yet. And we find that it's extremely important for non-i.i.d. generalization, which we'll show later. So what we do here is very simple. When you're encoding the question, you concatenate the question with the schema items from your knowledge graph, and you use a pre-trained BERT to jointly encode both parts. Then by doing so, you allow the question and the schema items to interact, and then you get question-specific contextualized encoding for the schema items and vice versa. And that turned out to be very helpful. So just some quick numbers to show why this is helpful. The QGG model is the previous best performing KBQA model from the literature, and we adapted to this new dataset. And we also proposed 2 new models. The transduction is essentially just a constructive semantic parsing, sequence to sequence. And the ranking model is like you first generate a set of candidates, and then you use a 6-to-6 model to rank the generated candidates. Here, we can see that when we are removing birds, we just use glove embeddings for the schema items. When we remove bird, there's a huge drop in compositional and zero-shot generalization in both models. But there is little to no drop in their i.i.d. generalization performance, which is pretty interesting. And it's easy to understand why it's very important for zero-shot, because when you have not seen a schema item during training, you really need some smart way for the model to identify and distinguish between the schema items. But for compositional generalization, it's less clear why it helps so much. I think the possible explanation here is that when you don't have good schema encoding, then the model tends to more easily overfit to the training data. And so that when it's asked to generalize compositionally, it's not doing such a good job. But when you have better schema understanding, the overfitting becomes less severe, and so that helps. But that's just a hypothesis. Okay, and we have a leaderboard and a data set and everything. So if interested, please check it out. So I think we're running out of time here. So I will just quickly go through the third frontier here, which is the new learning paradigm for training conversational AI called learning from use. And it's a joint work with Ziyu Yao and Yi Tang from OSU, and Ziyu is going to join George Mason as a faculty member, and also Scott Yi from Facebook AI Research and Huan Sun from Ohio State. And we'll be looking at the text-to-SQL parsing problem. So we started the motivation with the current life cycle of conversational AI development, which typically consists of 2 phases: pre-deployment and post-deployment, right? So in the pre-deployment phase, we want to collect data and bootstrap a system that is good enough so that we are confident that the users can start to use it. And then after deployment, we start to get real usage, and then we analyze the usage, maybe annotate some of them, and then to continuously improve our model. But it has several problems in this typical life cycle. First, of course, it's a high cost, because annotating this data for conversational AI is really expensive, because you need to understand both the utterance and the meaning representation and establish the correspondence. And also there is privacy risks at the post-deployment phase, because you need to look at the real usage, and this conversation data could be quite private and sensitive from real users. And then in general, these models, they act like a black box to users, so there's a lack of explainability and trustworthiness. So that motivated us to think whether there is alternative ways to build conversational agents. What we come up with is that after deployment, the conversational agent should have the ability to be introspective of its own uncertainties, and it can formulate these detect and formulate these uncertainties as questions to the user, and then so that the user could provide further feedback to resolve such uncertainties and get better parsing results. And at the same time, such interaction will provide us with targeted annotations to continuously learn the conversational agent. So that's sort of like a win-win. And at the same time, the user gets to know more about the decision-making process of the conversational agent. So it's slightly less black box now. And of course, because now we don't need annotators to look at the private user conversations, there's reduced privacy risks. So that's the gist of the approach. I think I'll skip this one. So basically how it works is that we propose this general framework that can work with many different base semantic parsers. So when we are given a natural language query, we will run the base semantic parser to generate a partial parse, and we will detect the uncertainties in the partial parse. If there is uncertainty, we will pass it to a question generator, ask the user a question, and then get the user feedback, incorporate the feedback to improve the results. There's a quick example. Let me see. So this is a table, and this is the user question. This user question is a bit ambiguous in the sense that this number one corresponds to the first column or the second column. So the agent has some uncertainty when predicting this column. Then we ask a question to the user. The user gives us some feedback. We can ask further follow-up questions. And then based on the user feedback, we can resolve these uncertainties and finally generate the correct SQL query. And it turns out by just doing something as simple as this, that by adding interactivity to these agents, it can already dramatically increase the test time accuracy. In fact, it improves the accuracy more than 10% with just 1 to 2 questions to users. But so far, this is just about interactivity. There's no learning from use yet. So in the 2020 work, we realized that such interaction actually naturally gives us like targeted training data to continue learning our agent. So I think I'll skip this, but basically we propose the imitation learning algorithm. If you're familiar with Dagger, the classic imitation learning algorithm, this algorithm looks a lot like Dagger, except that the training data, for the training data, we don't use expert annotations. We just ask through the interactive mechanism we had before, we directly ask users to provide the demonstration. And it turns out that the algorithm we proposed called the nail is very annotation efficient. So compared to the fully supervised baseline, which you have expert annotate everything, we use much less annotation. And these annotation, remember, they are from real users, not experts. So the other benefits are privacy and the cost. And we can get a pretty decent level of performance by just using such annotations. And if we just look at like whether our algorithm will lead to worse performance in general, we find that actually the gap between our algorithm and the fully supervised baseline is pretty small. And we have a theoretical analysis to show some bound between these two approaches. Okay, so a quick recap. We have talked about 3 emerging frontiers of conversational AI, representation and broad coverage, and the learning paradigm called learning from use. And of course, there are many other exciting emerging frontiers. Like we could try to make conversational agents more contextualized. Like you can know more information about the user beyond just the current dialogue history, and you can know users' long-term preferences and things like that, and incorporate that into planning. And we can have mixed. So currently, the agent is mostly, user initiative. The user is always the one who is initiating the action, but we hope to have more mixed initiative or agent initiative, where the agent can proactively engage with the user. And of course, there is a largely understudied bias and fairness issue in conversational AI. this is partly due to the difficulty of data collection for conversational AI. So, so because it's so costly, you can only afford to hire a certain group of people to annotate a certain amount of training data. So then most of the time, your training data will insufficiently cover the underrepresented groups. And as a result, your agent will perform less well on the underrepresented groups. So how to ensure the fairness in this case is still largely underrepresented, studied, but I think urgently needed issue to address. And finally, there is also the very interesting issue of challenge of learning within the compliant boundary. So like, for example, in Microsoft, you cannot, it's company policy that you cannot directly look at the user data. The user data belongs to the user. So you cannot even look at it, not to mention learn from it. So given these constraints, like how do you continuously learn your conversational agents with such private data? So that's a very interesting challenge. Okay, I think that's all I want to share today. Thanks for your patience, and I welcome any questions.
Okay, thanks. You really learned a lot from your talk about practical solutions to conversational AI. So we probably just have very short question answering time. So if you have a question, we probably can ask one or two of them to Professor Yu Su. Otherwise, please send email messages to Professor Yu Su in case you have more discussions to have. So I guess we are about the time. So several of us will have continued discussion with you in the afternoon. Thanks again for your very rich talk.